days of talks. Since this is the world's largest blackboard, I could not resist to probably give part of my talk on the board. I hope that's okay. I'll start with a couple of slides. So this whole topic of this talk came actually up when my student, back then still student, Andy Lee, showed up in my office and said, I think that the repulsive and the attractive Bose-Hubbard model, they look exactly the same. And I told him that that isn't true. And he explained a little bit more and had not a lot of intuition, but he said, well, I'll go back and I'll try and convince you. And he came back a week later and had some calculations. And so I think he's right in a very specific way. And I'll try to show to you in what way attractive and repulsive Bose-Hubbard model might actually look the same, and how this also generalizes to other types of problems in driven and damped systems. And I'd like to start with a little bit of maybe background of where did all of this come from. So my background is a lot in superconducting qubits, and I'll tell you a little bit about that. Then I'll show you the specific case of Bose-Hubbard dimer, and how you can see that repulsion and attraction are actually not so different. And then in the third part, I'll show you how to generalize this and put this in a somewhat more abstract language that then might also apply to your favorite Markovian open quantum system. So if you're not in the field of superconducting qubits, I'll just say a few words. I'm sure that if you're around next week still, you'll hear a lot more, in part by Michel Deboré. But the story is that since the early days of superconducting qubits have become a lot better. So coherence times have grown over the years by something like 5 orders of magnitude, and they're still increasing. And so by now there's actually interesting games that you can play. In fact, if you or your student is interested in playing with a quantum computer, I believe that IBM now has opened the access to the 16-qubit machine, and so you can talk to a quantum computer online and actually run little algorithms and do science with that. The basic building blocks in all of this is something that you've heard about multiple times now. Our circuit-QED system is, again, symbolically, it's just a pseudo spin, right? And it's coupled to a microwave resonator, which you can drive. And it's an open quantum system because photons can escape from the resonator, and this pseudo spin, which is our superconducting qubit, that can lose excitations. On a chip, that kind of structure might look like this, where the big picture here is that's at least the start of your coplanar waveguide resonator with the center pin here and ground planes on the top and bottom, and then in a place where probably it's close to an antinode of the field, you have a superconducting qubit, which might look like that. And if you're not familiar with them and this looks kind of strange, don't worry. You'll hear more about it next week, I'm sure, and it's not particularly important for what I want to say today. So I already mentioned that people are using these things and doing research towards quantum computation. There's some other cute ideas how to make use of qubits and resonators, and one is to try and understand open quantum systems better. And so just to set the stage here, you've seen this as well already. So the picture here is that you have your qubit or resonator qubit system, and you're interested in its dynamics, but this system couples to a bath. And what I'll be talking about, everything is going to be weak coupling to the bath, so that you can describe the dynamics in terms of a Lindblad master equation. And here's the general structure of that. And so the question is, if you have qubits and resonators, you can couple them together. Can you maybe couple many of them and then investigate something that people have been calling dissipative phase transitions. And those dissipative phase transitions are, you can think about them in terms of this super operator L, which is on the right-hand side of the master equation, because with that you can make a very nice table, first to be found in this paper by Kessler et al., where on one hand we know a lot about quantum phase transitions, where the quantity of interest is your Hamiltonian and its eigenstates and eigenvalues, and in particular the ground state. And the phase transition happens when you tune some external parameter and your ground state at some point actually switches over to a different one, and that is where your zero temperature quantum phase transition happens. And for dissipative phase transition, the object that you're investigating now is this super operator L, happens to be not Hermitian, which makes things interesting. And still, you might ask about the possibility to change some external parameter and ask, well, if you now look at the eigenvalues of this super operator in the complex plane, then as an external parameter changes, they will move, right? Each of them in a particular way. And it could be that for a particular parameter value, there's one that not just approaches 0, which is where the steady state sits, but then actually switches over and takes on the role of being the new steady state. And so the state of the art in terms of experiments is perhaps this one here, where Andrew Houck's lab looked at a device that had 72 microwave resonators, each coupled to its nearest neighbor and to its local transport qubit. And just to give you a flavor of things that can be observed in this experiment, so they look at transmission through this long chain, they feed in microwaves on one end, look at what's coming out at the other end, and at low power, they just see resonances. Those are the resonant modes of this linear chain. The qubits are off-resonant. But as they increase the microwave power, something happens, and you can tell that at some point something pretty drastic happens where the transmission drops off pretty drastically. In fact, if you come from the bottom, come from low power and go to the top, you see that this transition happens in a different spot than in the case when you go downwards in power. And so there's hysteresis. You can ask, well, can you switch between these two states? And yes, you can. And they observe that the switching rates are very, very low. So the typical dissipation rates that they have are sitting up here at 10 to the 5, 10 to the 6 hertz. And then at the phase trend, the switching between those two metastable states that happens once a second or so. And so there's lots of questions you could ask. Is this what is quantum about this phase transition? But that's not really what I want to talk about. This is just setting the stage for why do we think about these driven damped systems at all. And so the story of this switching from repulsion to attraction starts with the Bose-Hubbard dimer. Is this the right thing to use? All right, so let's talk about the Bose-Hubbard dimer, which is just bosons that can hop between two sites, and they interact. So that the Hamiltonian in the positive and negative U case just looks like this. So there's a sum over two sites, same on-site energy omega, and then I'll use notation which by the subscript tells me whether the symbol corresponds to a positive or a negative Hubbard U. And then there's the hopping that is still missing. And so maybe the first thing that we can quickly do is we can ask, well, what does the system do if we don't drive it? What is the ground state? And so ground state for fixed n, large compared to 1, and to make my life easy, I'll assume that n is even. Then, let's assume that also u times n squared is large compared to j times n, which is what I should compare if I ask about how do hopping and interaction compare to each other. Then, for the positive case, we'll find that separating bosons lowers the energy, right? They repel, and so the ground state should look close to this, where on each of those two sides there are n/2 bosons. And for the attractive case, bunching up saves energy. And that means that, well, I'll first write G1 approximately N0 and G2 0n, and then if you look carefully in high order perturbation theory, those two will actually hybridize. But still the physics, negative u, positive u, is clearly very different. So now comes the point where we should switch to considering bosons that are driven and damped in the following way. So we'll take our Hamiltonian from just a moment ago, and we'll add a drive term, which I'll already write down in rotating wave approximation. So that once we switch into a rotating frame, I can write down an effective Hamiltonian for those two cases that looks like this. For completeness, I will write it down. That gives you a moment to just take a breath and stretch, perhaps. So the delta omega now is the detuning between the on-site energy and my on-site frequency, drive frequency. E is the interaction term. And the drive term now has become time independent, which is good. I think in my case here, I'm interested in just driving site number 1. And I have a hopping term to copy and paste. All right, and clearly in order to include photon decay, we'll stick this into our Lindblad master equation. And you remember that that's just negative I commutator of H plus minus, I'll drop the effective for now, rho. And then plus gamma. And then the photon decay has the form AN rho AN dagger minus 1/2 rho plus minus AN dagger AN anticommutator. All right, very good. And so now, how could I get an idea that dynamics of this is the same, or if there's a very close relation between the case where I think about positive u and negative u? And so the the suggestion I would make is we pick an observable and test what happens. So consider, for example, the expectation value of A1. So in an experiment with a resonator that could correspond to measuring the voltage, and I'll do that for the positive U case. Then the equation of motion that you get either from the master equation or by other means is I time derivative of expectation value of A1 is frequency detuning minus I gamma over 2 expectation value A1. Then comes the interaction term 2U plus. Jonathan didn't clean the board for me. A1 squared plus J. This is where the hopping comes into play, and then we have the contribution from the drive. And so now let's do something very simple. Let's see what do we get if we take the complex conjugate of that equation. So clearly that means I have negative I d by dt A1 complex conjugate delta omega plus I gamma over 2 A1 complex conjugate. This term here, there's no I around, so I'm only going to take the complex conjugate of the expectation value. Likewise here. And I assume that my drive strength has no phase, so it's just a real number. And now in step number 2, we'll just shuffle this minus sign back over to the right-hand side. So I'll do what students always hate. I'll do the erase directly on the board. It's here. This one turns into a minus sign. This one turns into a minus sign. Minus. And note that according to my notation, this I could actually just write as plus 2 times a negative u. And I'm pointing that out to emphasize that this equation here now looks very much like the equation that I would have written down if I had started with a negative u model, right? Except for the fact that I've switched signs of my Hamiltonian parameters delta omega, j, and epsilon as well. So find that, well, allow me one step in just notation so that I don't get us confused. So I like to bunch up my Hamiltonian parameters in, let's call it a curly P. So that collects all my Hamiltonian parameters, which in the positive U case were U plus, delta omega, epsilon, and J. And with that notation, I can now say that A1 plus evaluated for parameters P, that's what I would just like to denote as A1 P plus. And with this somewhat awkward notation, we can easily write down the relation between the positive and the negative U case. Namely, we find that if I consider the expectation value of A1 for parameters P, and I take the complex conjugate, then I actually get the expectation value of A1 for the negative Hamiltonian parameters, which also means that U is now negative, and analogous relations for all operators of the form A1 dagger to the power P, A2 power Q, A1 PQR S. This last bit I haven't shown, that's a little bit more tedious, but clearly you have to convince yourself that this works for the entire hierarchy, because in your equation of motion for expectation value of A1, you get an expectation value of this operator, and so this sort of relation works for the entire hierarchy of operators of this form. So that's interesting, because that means that if I have a system, a Bose-Hubbard dimer that is repulsive, then with system parameters Q plus, which clearly is positive, delta omega, J, and epsilon, damping rate gamma J. Did I give them different ones? No, just one. And expectation values A, we can map this to a partner system where the U and the other Hamiltonian parameters have changed signs. Damping rate is still the same, and expectation values for the system 2 are the ones from system 1 with the complex conjugate. Note that this sign here is irrelevant. I can gauge that away, for instance, by mapping A1 to negative A1, no problem. And then this sign here also goes away. The only thing that could possibly change is my detuning. So if my positive U model was driven with a blue detuning, then to get the same result for negative U, I should use red detuning. And we can quickly check that this indeed works when we do numerics. Is it possible? Yeah. If we can we roll it down just a little bit, perhaps? Maybe this is already enough. Yeah, that's good. So this HSI just stands for Hamiltonian sign inversion, and you'll see in a moment that that is what happens generically. Here, Andy looked at the case with positive U and looked at the examples here are photon number on side 1 and side 2. He chose some initial condition, perhaps this was with photons on both sides. And I forget what the exact initial condition was. The point is that repeating this numerical experiment with the same initial condition, but delta omega adjusted as well, you get the same result for negative U. So just by looking at what is the system doing, so just observing expectation values, you won't be able to tell whether I'm presenting you with a positive U or a negative U model. All right, and this is in part interesting because people have actually looked at the driven damped Bose-Hubbard dimer. So here's a paper from Mohammad Hafezi's group, and they determined that certain parameter range of J and U, you can find symmetry-breaking steady states, and they only presented results for positive U. And now with this insight from this mapping, we can basically just flip their phase transition diagram and know immediately that the corresponding thing also occurs for negative U. Yes? can maybe I'm not quite sure what you're suggesting. So you want to do.
No, so I just want to change A to minus A1 to minus A1.
Yep.
And then the overall, from the overall Hamiltonian, I want to take a minus sign out. Then I get basically H plus with this A2 minus A, H plus is equal to some minus H minus or something like that.
Maybe it'll be good to discuss that offline, but I'm pretty sure that so we probably agree that in the equilibrium situation, right? Positive and negative U do give different ground states.
No, so yeah, so the now whatever was the excited state will become a ground state. So it will become, the energy spectrum will become flipped.
That's right.
Yeah, so because H has become minus H.
That's right.
So now you have a different ground state, but you can see that from the Hamiltonian itself.
Indeed, indeed. And we'll see in a moment how we can do this in a general way without going through equations of motion in a somewhat complicated way. But I found this a nice way to see that indeed at the level of equations of motion you see that there is this mapping, and it's just complex conjugation at that level. I think I'm going to switch to the board again at this point. So in the general case, we'll make use of the time reversal operator in a certain way. So the general Hamiltonian sign inversion mapping goes as follows. So we'll consider a system Q1, which is described by a generic Lindblad master equation. You've seen it multiple times now. CJ is my jump operator. And I'll assume that the Hamiltonian is time reversal symmetric. And so it'll be good to remember that that means we can write T H T dagger is T, where according to Wigner's theorem, T is an anti-unitary operator that can be written. Sorry, that's a good point. This is supposed to be H. Thank you. So T can be written in this form. So the ends here form an orthonormal basis, and I want my unitary to the left. And this operation here means complex conjugation. Okay, so with that, we'll consider the object rho t, defined as t rho t dagger, and note that this is not backwards in time evolution. So if you were to watch the movie played by rho t of t, that's not rho going backwards in time. Well, one thing that one could also formally prove first, I'm not going to do that here, is even though one t is antilinear, once you sandwich rho in between two, you get back something that is linear. We've already assumed that this happens over here silently. And so we can now ask, well, what is the equation of motion obeyed by this object? Well, that's not hard to get. So what we would do, right, is we would take this equation of motion, sandwich it with t and t dagger, and try and simplify. So in the first step, we put the full right-hand side here, and your t and t dagger, and after just a few steps, what you'll get is just this. And then allow me to write this in somewhat abbreviated form, where this D symbol means that spits out this thing, where the jump operator is what goes into the brackets. This is similar. It's not quite your Jonathan's curly or script L, but almost. So Cj goes inside, and then this gets applied to my density matrix rho t. So this is a Lindblad master equation. Where, as you pointed out, the Hamiltonian now is the negative Hamiltonian, and I've forgotten to change my jump operators. T dagger, because those, in fact, can also change if they are not time reversal invariant. And so that's good. That means that this indeed allows us to have a mapping between a system with H and negative H. Let's take a look at what happens when we calculate observables. So for instance, I could ask what happens if I want to know what does this system number 2 do when I measure the observable A. So that would be trace A rho t. And now you can test whether or not you're awake. Is it okay to just pull this T over here? Nope, it's not. Was that you? What was that? Indeed, that's not okay. So you can convince yourself that what happens is you will pull it over, but you'll gather up an additional complex conjugate. And one easy way to do that is to work with this representation of your time reversal operator, where this U is a unitary matrix. So the result is trace T dagger A T rho without a T complex conjugate. And so with that, we have a complete dictionary for that mapping. So we have a system Q1 with Hamiltonian H, damping rates and operators. So Q1, Hamiltonian H, and damping rates and operators gamma j and cj, and expectation values that sort. And then, well, we can do it this way. We've mapped this or directly related this to system Q2, which now has the negative Hamiltonian, same damping rates, possibly modified jump operators, and expectation values that are obtained from the ones in the first system by applying time reversal operators and taking the complex conjugate. So that means that clearly this mapping is not limited to Bose-Hubbard dimers. And one thing that you could possibly find interesting as an application is a driven damped spin lattice. So here's one. It's a very simple one. It's all sigma z. I've not done anything fancy here, but there's geometric frustration because at least possibly for the correct sign of j, because I've chosen a triangular lattice, right? And so again, the ground state physics would look very different for positive j and for negative j. But if I switch to the driven and damped spin lattice and apply this mapping, then I find that there's actually, in the dynamics, I'm not going to see anything special coming from this frustration. And again, you can, if you don't believe it, you can do numerics and check for whatever expectation value you want. You start with an well-defined initial state, you let the system evolve, and you observe the same thing in both cases for both signs of j. And so that's pretty much all I wanted to say, I think. So let me just quickly summarize this. You see the mapping up there once again, and we're thinking a lot about various applications. Right now, we're mostly focused on exploring different non-equilibrium phase diagrams, both those that we've looked at in the past as well as those that other people have studied. And I think it's a nice mapping that potentially has applications in many different contexts, because there's really nothing that ties this to qubits or resonators or any of that. As you can tell from the way that I tried to present it, it's just Lindblad master equation in its most basic form. No. The ground state, where the system will go when you take away the drive, it will go to the vacuum state. There won't be any particles left. What you're thinking about is the case where you have some fixed particle number.
No, just one thing is this Bose-Hubbard model with negative U, that does not have an energy minimum, right? So is that some sort of pathological?
That's a very, very good question. So indeed, when would a negative U Hubbard model be even realistic? So I know one example. In fact, when you couple a superconducting qubit, the flavor being transpond qubit, to a resonator, then that would induce a negative U, but only over a certain range in energy. So it's a low energy or low number of excitations approximation, which if you go above a certain number, then the Hamiltonian would change. There are higher order terms beyond that then make the original Hamiltonian bounded from below.
Yeah, but so if you connect such a system to a bath, then I think it will attract things instead of, I want it because that is like more favorable. I mean, what I'm saying is, if you start with a small number of things where sort of that negative U approximation is good, then you will basically, if you connect it to a bath, then it will take things and it will go to some place where you cannot still do the negative U approximation.
Don't forget that for photons, there's no particle bath. There's finite temperature. So yes, you can get some thermal excitation, but there's no grand canonical ensemble. This was just meant as here's research that motivates us to actually think about something like a driven damped Bose-Hubbard model. So there was no relation that says I'm explaining these experimental observations with what I've written on the board. This was just background. These are things that we have worked on, but not this mapping is not meant to explain this. So down here, there's certainly a description that where dispersive approximation and resulting Bose-Hubbard would be appropriate, but as you go up higher, the drive power, as you see, increases over several order of magnitudes. And at some point, there are so many photons in the system that you go beyond the critical photon number. Dispersive approximation breaks down, and it's not appropriate anymore to approximate your Jaynes-Cummings type lattice with a Bose-Hubbard lattice. You mean this? That's a really good question. So the cases that I'm familiar with, the jump operator actually does not transform in an interesting way. So I think in the case of something like annihilation operator A, nothing happens. So it would be pretty neat if there were physically relevant examples where there is a transformation. So at this level, I don't think I have to make any assumptions on the drive. Now, what I do have to check, of course, is does this describe a physical system, right? So in particular, if you consider an infinite Hilbert space where you're worried that I can't truncate it, and so the example from up there was negative U, it's unstable, right? If you face a situation where you can't truncate your Hilbert space, you've generated a Hamiltonian that is not bounded from below, then clearly you've generated something that is unphysical, right? Now, fortunately, in most cases that I deal with, my infinite Hilbert space can be safely truncated, or in the case of pure spin system, it's even finite. So the not being bounded from below does not always come up as